All right, everyone. Well, thank you for coming back. This will be our last lecture in thermodynamics. So that's exciting, right? We'll have one more course review. We'll talk about Brayton cycles today. And, right, so we've gone through these other reviews. We talked about diesel cycles. We talked about Rankine cycles. We did a turbojet. And now we're going to do a Brayton cycle. So these are kind of the cycles that we might see on the exam in addition to the Otto cycle. Right? And we didn't do a review for heat pumps and refrigerators, but again, you can go back to the lectures to get information on that cycle as well. So Matt has kindly gone through and found a question for us, so I will start to bring that into my notes here. So let's go to the desktop. We will save this. Open. Copy. Yes, I'm narrating this. It's super exciting, I know, right? So it is this cycle here, chapter 9. This is the one that we were looking at. Is that true, Matt?
Yep, sorry.
Okay, no, that's okay. So here, right, so we can go through this one, and this is kind of the 4-part one, and then we can talk about maybe the things that make, the different things that we can do in a Brayton cycle, right? So here, right, there are these 4 components. So we have here a compressor, a heat exchanger, a turbine, and then another heat exchanger. So if we were making a state table, in this case, we have 4 different potential states. So I will, can I get rid of this? Delete cells. Oh, actually, yeah, 4 states, right? And one is a turbine and one is a compressor. So that means that when we go between state 1 and state 2, this is our compressor. Then we have a turbine, so this could be isentropic and then real as well. And we'll talk about how to deal with both of those 2 things, right? So here, right, there's a couple of things that we need to know. So here it wants us to find the thermal efficiency and the back work ratio and the net power. And of course, we would need to find the net power to find the thermal efficiency anyway. Right, so here, if we want the thermal efficiency, we have to say, what's the energy benefit? And because this is a heat engine, the energy benefit is going to be net work, and the energy cost is going to be heat in, right? Now, because if I look at this component, the mass flow rate through each one of these different components is the same. So I can also write this as little w dot net divided by little q dot net. Oops. We'll pretend that's a t. Right? The back work ratio. Now remember, back work ratios for Rankine cycles tend to be fairly low because it doesn't take us much power to increase the pressure of a liquid. But in a Brayton cycle, right, we got to ask ourselves, what's the working fluid? And the working fluid in a Brayton cycle is some ideal gas, which we'll assume is just air, right? So now our back work ratio is going to be the power from, in this case, the compressors, which are just like pumps, divided by the power of the turbines. Now, if we got both of these things from the first law, we would find that compressor power is negative and turbine power is positive, but the back work ratio we want to be a positive number, so we'll take the absolute value of all of that. And this is basically acknowledging that the power plant is the first consumer of the power plant. And actually, one of the neat things with the Brayton cycle is that there's a physical shaft that's going to connect the compressor and the turbine. So physically, as the turbine is spinning the shaft, it's powering the compressor. That's a little bit different than in a Rankine cycle where you're putting power into the grid from the electrical generator, but then you're plugging the pump into the grid too. So even though they're both The power plant is always the first consumer of the power. Here they're physically connected. The third thing is going to be the net power in kilowatts, which I guess here we don't necessarily need to know the net power because we could get the net power per unit mass, right? But we sort of need that for the first part anyway. But here W net is going to be, and I'll color code this because again, I like to get all this stuff from the first law. So I'm going to get the sum of all the turbine powers, and that will be positive. And then it'd be plus the sum of all the compressor powers, and those are going to be negative. Right? So here, if I wanted to get, so I kind of have a symbolic solution for all of these parts right now, but the problem is I don't really know anything. Right? Which, I don't know, you want to say that out loud too much, right? But here, like I don't know the net power, although I have this expression, but here I don't know the turbine power. I don't know the compressor power. I don't know, oh, this shouldn't be Q net. This should be Q in, right? Q dot in, but I don't know that, right? And again, I don't know the compressor power and I don't know the turbine power. So none of that's all that good, right? So it's nice that I have an idea of how to solve this problem already, but I still have some work to do, right? And because it's thermodynamics class, the thing that we want to do when we have terms like a W dot or a Q dot is we want to go to the first law, right? Now, whenever we use the first law, we got to ask ourselves, one of the other big questions that we talk about for these cycles is, are we going to think about these processes as open processes or closed processes, right? So in this case, because the mass is moving from component to component in order to do one of these processes, then this is an open system, right? And here, as we're doing this, we've physically drawn in a heat exchanger here for the heat rejection, but this doesn't really exist in the system, right? So here the turbine is going to exhaust out to the atmosphere, and then we're going to pull some air in from the atmosphere into our compressor. So in a sense, it's the environment that's our heat exchanger here, right? So we have these four components, even though one of them is kind of not actually there, right? It's kind of like a pseudo component here, but the mass is moving, from one component to the next component in order for us to do this particular cycle. So that means it's an open system process, right? So here, for all of our components, we'll say they're at steady state and that there's no change. So this is delta KE is equal to 0, which is equal to delta PE. So I'm also going to cancel this out. For all of our components, these are just one inlet and one outlet. And then depending on the component, right? So here I'm going to assume I'm going to say that for the turbine and the pump, well, here, how about instead of doing that, I say for the turbine and the compressor, we'll pretend that's a C, they're going to be adiabatic. So Q dot will be 0. But for the heat exchangers, right, so for the combustor, I'll call that CM for combustor. And then for the environment, which is the other heat exchanger, we're going to assume that those are passive. So W dot is equal to 0. So if we do that, then anytime we have a W dot term, right, so if we have a turbine, right, this is going to be M dot times H in minus H out. So now here in this particular cycle, there's one turbine and there's one compressor. So here, my turbine, the inlet is H3 and the outlet is H4. So this is going to be H3 minus H4. My compressor, oops, let's see if I can do this here. W dot C is going to be, it's also going to be M dot in minus M dot out, but now the inlet is H1 minus H2, right? And here we expect this to be positive and we expect this to be negative. Now, if I'm trying to find the heat transfer, Q dot in happens between state 2 and state 3. So this is going to be m dot. Now, if I use the first law to try to get Q dot, this is going to be H out minus H in. So this is going to be H3 minus H2. And I expect this to be positive as well, because heat in is positive and heat out is negative, right? So then my heat rejection, so this is my heat out, is going to be m dot. Now here, the inlet is state 4 and the outlet is state 1. So this is going to be H1 minus H4. And that one's going to be negative. So now there's a couple of things, right? So if I put these back into my equations that I have up here, right, then for this one, right, the mass flow rates are going to drop because all of these components are one inlet and one outlet, and they're all chained together in series. So the inlet for the compressor is the outlet from this heat exchanger called the environment, right? And, you know, as we keep going through, so there's really only one mass flow rate in this whole problem, right? So anytime I have a W dot term divided by a Q dot term, I can use capital W dot or capital Q dot, but I can also take out the mass flow rate and use lowercase w dot and lowercase q dot, which in this case will be just delta H's, right? So here, this first term, my thermal efficiency, is going to be my net work, which would be H1, let's see if I have enough room, minus H2 plus H3 minus H4, right? And then my heat in is going to be over here, and this is going to be H3 minus H2. My backwork ratio, this is going to be, because again, the mass flow rates here are the same. So from my compressor, this is going to be H1 minus H2, although that's a negative number. So I'll have to remember to take the absolute value of all this. And the turbine is going to be H3 minus H4, right? And here I'll take the absolute value. Now my net work is going to be the mass flow rate times my compressor power. So this is H1 minus H2 plus my turbine power, H3 minus H4, right? And now I'm going to expect this part here is going to be negative and this part here is going to be positive. So when I look at all these expressions, what I know is that I'm at the point where I like to be in thermodynamics. All of these things are a function of the specific enthalpies. So that's good because that means all I have to do is fix the states, right? Or all I have to do is fix the states, right? Fixing the states can be a pain. So here, let's see what information that we have. So we know at state 1, it's 100 kilopascals and 300 degrees Kelvin. So 100 kilopascals, 300 degrees Kelvin. At state 2, I don't know too much, but it tells me that P2 is 10 times P1, right? Or P2 over P1 is equal to 10. So P2 here, this is going to be 1,000 kilopascals, which is 1 megapascal. That's true whether I go through the ideal turbine or the real turbine. I'm going to assume that as I go from state 2 to state 3, that process happens at constant pressure. So this is also going to be 1,000 kilopascals. But here at state 3, they told me, sometimes they will explicitly show you this, like they do here. Sometimes they'll say the biggest temperature, or the highest temperature in the problem is 1,400 Kelvin. So it's nice to be able to draw these TS diagrams because here you see the maximum temperature, right? So now, right, so this is, what did I say, 1,400. And now as I go through, because I know that the turbine exhausts to the atmosphere, or if we're pretending that it goes through this heat exchanger here, this heat exchange process we're also going to assume happens at constant pressure. So P4 is going to be equal to P1, just like P2 is equal to P3. So here, if I'm looking for P4, this is going to be 100, whether I go through the real turbine or the ideal turbine. So I'm not sure if in this problem, if they tell us things like efficiency of the compressor or if they don't, right? Or I'm not sure. So on an exam, we're going to tell you, because now we're at a choice, right? So we've got these expressions and they're all a function of these specific enthalpies, right? So we're at the point where we've used the first law, right? So we can continue on in the problem, but only after we've decided whether it's constant specific heat. So if it's constant specific heat, then that means that delta H is going to become Cp times delta T, or it's going to be variable specific heat, and then delta H just remains delta H. So does anybody have a preference how we talk about this? Whether we go through with constant specific heat or variable specific heat?
Do you know which one would be harder?
It's funny because I think that when you look at it, it's a good question, right? I think that it's less work to do constant specific heat. I think in both cases, you're going to want to look for the isentropic processes. It might be because I know how to do it both ways, but I don't think one way is harder than the other, although I do think variable specific heat requires more effort. I saw that Jack was unmuted for a second too. I don't know if he had a comment to make.
I was going to say, wouldn't it depend on what information you're given for which one's harder?
Well, maybe, because you might not be given these constant specific heat values, which for the problem sheet that I took this for, the one that we did in class, I just had them out. So if you weren't given constant specific heats, then I guess that's another thing you'd have to look up.
Mm-hmm.
So I don't know exactly if that answers your question or if there was something specific that you were thinking about.
No, that answers it.
Okay. So I think just because I don't want to be flipping back and forth between the state tables, that I'll talk about this in terms of constant specific heat, but I can also show you the process, the same process that we would use if we did variable specific heat. Does that sound reasonable?
Yeah, sure.
Seems pretty good.
So the nice thing about constant specific heat is if it's constant specific heat, the only things that I need to find are the temperatures and the pressures, and I've already gotten all the pressures, right? If it's variable specific heat, then I'm actually going to have to, so if this was variable specific heat, then I'm actually going to have to go through and find this. And I'll talk through that process, right? So if you get, so a Brayton cycle problem or a turbojet problem or a diesel or an Otto cycle problem where the working fluid is air, you'll have to make this decision. Are you going to use constant specific heat or variable specific heat? And anytime the working fluid is air, it's really important to know what these isentropic processes are, right? So if it's a cold air standard problem or constant specific heat, then we're going to choose, when we do isentropic processes, to use one of these three equations. I think I rarely, so this is rare, I almost never use this equation. It's on the equation sheet, and if you want to be able to express the pressure ratio as a volume ratio, you can use this, right? I guess first, the other thing we got to remember is that K is equal to Cp over Cv, right? So now, if it's an open system process, then you're going to know the pressure ratios usually, right? So here, I use this particular expression if we're talking about a Brayton cycle or a turbojet engine. And I use this particular expression if I'm talking about an Otto cycle or a diesel cycle. And that's because in that Otto cycle and diesel cycle, when the piston is moving up and down, I know about the compression ratio, or I know maybe the cutoff ratio in a diesel cycle. So the volume ratios in the cylinder or the piston cylinder assembly are important, right? But volume ratios make less sense when we're talking about open system processes, where we'll normally know the compressor pressure ratio, right? So they told us this, right? They told us that P2 was 10 times what P1 is. So usually in these open systems, we're going to know these pressure ratios. Now, this is also true. So this is constant specific heat, right? But if we were going to do variable specific heat, we'd also be looking for these isentropic processes to try to figure the problem out, right? So again, the one that has the pressure ratio, we're going to use that for Brayton cycles and for turbojets. And the one that has the volume ratios, we're going to use that for Otto cycles and diesel cycles. But the other thing that we need, if this was going to be variable specific heat, is we would also need table A22 or A22E. Because what would happen is, right, if you remember that table, it's got maybe temperature, it's definitely got enthalpy, it's got specific internal energy, and then it's got like VR and PR, these reduced pressures and volumes. And what happens is, in this case, if we know the ratio of pressures and we can fix the first state, then we can get PR2. And once I have PR2, then I can go back and I can find H or I can find T, right? Or if it was an Otto cycle or a diesel cycle, I would use a volume ratio. Usually I'd know VR1, and then maybe I'd get VR2. And then if I had VR2, I could go back and find specific internal energy, or I could find temperature, probably both, right? So it's important to know first what the isentropic processes are. Then it's important to know, is it constant specific heat or a cold air standard, or is it variable specific heat or an air standard analysis, right? And then we're going to know, is the system open or closed? And that's going to tell us, do we want a pressure ratio or a volume ratio? So this one is maybe a little bit easier to do in the class because I don't have to flip back and forth on the different tables and do the interpolation, right? But I'll talk about how you would do that, right? So now what we got to do is we got to find out which of these processes are isentropic or could be isentropic. So the trick, right, is that the isentropic processes are the ones that happen when we're saying it's adiabatic and it's ideal, right? So the ideal turbine and the ideal compressor are going to be our isentropic processes, right? So that means as I'm going from state 1 to state 2S, delta S is equal to 0. And as I go from state 3 to state 4S, delta S is equal to 0. So here, what I'm going to do, I'm going to copy this because we'll use it later when we, I wonder if, yeah, it looks like it'll all copy. When we talk about the variable specific heat method 2. I'm still trying to learn exactly how this works with the writing and where the writing works, right? So here, if we're doing constant specific heat, all we need, sorry about this. So if it's constant specific heat, all I need are the temperatures and the pressures. I don't care about the rest of this, right? So I can just draw a line through all this other stuff. I don't care about it, right? So now here, all I got to do is find the isentropic processes. So here, as I go from state 1 to state 2, S, then what I'm going to do, here, I'm going to give myself some space over here. So from state 1 to 2s, this is isentropic. So because this is isentropic, I can go down to my equation sheet down here, and I see that T2s divided by T1 is going to be P2s divided by P1, all to the k minus 1 over k. Right? So let's see if I remember that. That's T2s over T1 is equal to P2s over P1 all to the k minus 1 over k. Now here, because I know the compressor pressure ratio, right? No, it's not easy for me to say, but I know these two pressures already. And I know, so here, like I know T1, I know P2s, and I know P1, right? I also know K, right? K for air is usually 1.4. But it's always going to be Cp divided by Cv. And in this problem, it was given to us. If not, I think in the textbook you can look it up, I believe on table A1. But I'm not 100% sure, but there's definitely a table where you can look up specific heat values. So here, I can recast this equation or isolate T2s, right? And that's going to be T1 times P2s divided by P1 to the k minus 1 over k. So if I do this, the good news is now I found T2s, right? But none of my equations had T2s in it, assuming anyway that that these turbines and compressors are real, right? So now I got to go through the real compressor, right? So now I got to remember something about compressor efficiency. So this is going to be delta H divided by delta H. But I got to think. So remember, the compressor, we're putting energy in to the fluid, right? So this is an energy cost. So the universe is going to make us pay more than we would in the real case, we pay more than we would in the ideal case, right? So here, the ideal compressor is going to go on top, and the real compressor is going to go on the bottom. So now this is going to be, because the mass flow rates are the same, this is going to be H1 minus H2s divided by H1 minus H2, except now we've already said that this is going to be a constant specific heat analysis, right? So now I'm going to take out the specific heats on the top and the bottom. So this is going to be T1 minus T2s divided by, so this would be Cp, T1 minus T2. So now there's a couple ways this problem could ask this, right? So if they didn't give us enough information to find the, so either they could tell us the compressor efficiency. So if we knew the compressor efficiency, then, we know T1, we know T2s. So then we could find T2. But I could also ask you on an exam, I could give you T2 on a state table and then ask you what the compressor efficiency is. So usually we would either not know T2 or not know the compressor efficiency, but we would know all the rest of this. So we would know one of these two things and be able to find the other. Oftentimes, this is what they would give us, and then from this, we would get T2. So that's kind of on the way going up in the cycle. Coming down in the cycle is basically similar, right? So here, we don't really need to know anything going from 2 to 3 because they already told us everything we need to know about state 3. Although I guess we did have to know that when we did this, right, as I went between state 2 and state 3, I did have to remember that delta P was equal to 0 here. So I had to remember that I'm assuming that there's no frictional losses or no pressure loss in the lines as I move between my my different components here, right? Or even as I move in that combustor, right? So now I know state 3. So now I got to go from state 3 to state 4s, right? So this is through the ideal turbine. Now again, I've recognized that this is an isentropic process. So T4s, which as I'm trying to find, divided by T3 is going to be equal to P4s, which is really the same as P4. So I don't necessarily need the S in the subscript here, divided by P3 all to the K minus 1 over K. Right now, just like in the, notice here, it doesn't matter whether or not I invert this as long as I do it inside the brackets as well, right? So here, notice that, so here I can see that T4s is equal to T3 multiplied by P4s over P3 all to the K minus 1 over K, right? Now, the only thing that I don't know here is P4, right? So then I can use this to find, or the only thing I don't know is T4s. So now I found T4s. Now I would want to go through the real turbine. And now I'm going to use the turbine efficiency. Now I got to remember that for the turbine, right now the turbine is a benefit, right? It's not a cost. The power out of the turbine is a benefit. So the universe makes it so the benefit we get in the real case is less than the benefit we would get in the ideal case, right? So here we always have to have these efficiencies be less than 100%. So the ideal turbine goes on the bottom because it's going to produce more of the benefit than the real turbine. So this is going to be H3 minus H4 divided by H3 minus H4s, which, if this is constant specific heat, right, which I guess I could write here over the equal sign 2, this is going to be T3 minus T4 divided by T3 minus T4s, right? And just like in the last part of the problem, we could, so at this point, I know T3 and I know T4s. I could construct this problem on an exam to get you to tell me the turbine efficiency or to get you to find me T4. So here we have now found all the temperatures here, right? So now if we found all the temperatures, then I can convert all of these expressions, all the delta H's here, to CP's times delta T's. I get rid of the CP's because it's going to factor out of all the numerators and all the denominators, except here. I guess I don't see where they tell us the mass flow rate in this problem. So I don't know that we can find this without knowing, maybe if they told us how much heat was rejected or how much heat came in here, maybe we could find this. Or maybe it would ask us for little w dot net, which is going to be big W dot net divided by m dot, right? So remember, there's different ways we can find mass flow rates, typically by taking the area times the velocity divided by the specific volume, or by looking for a place where we know a power or a heat transfer, or by having a component that has more than one inlet and more than one outlet. So we can use the first law to get a ratio of mass flow rates. And if we know one of those mass flow rates, then we can find the others if we can fix all the states. So that's basically how you do this problem if it was constant specific heat. Now, the general process is kind of the same if it's variable specific heat, except we do something a little bit different when we find the isentropic processes. Oops, that was a pretty terrible line, right? So these are the keys, right? So delta S is equal to 0, delta S is equal to 0. It's these isentropic processes that are always the key, right? So once we get to this part, that's going to be all the same no matter which method we're using, constant or variable specific heat. So if this was a variable specific heat problem, I'll show you how I would do this. So you'll see here there's more work. So now we'd start at state 1. So now because I know T1, I would go to table A22, and from that I would interpolate to find H1, and I would find PR1. So here I know that little v is on this, but here I'm going to say PR, so the reduced pressures, because that's the right? I know that for the isentropic processes, the ratio of the pressures is going to be the same as the ratios of the reduced pressures. So now for state 1, I know H, I know PR, and if I want it, I can also find S, right? So I guess here I also have to find the specific entropy. Although a specific entropy might not be on that table. Let's see if I can find the table. Because we're going to use, I don't think it is, right? It's on the table. We don't get this, right? Because on the table, they have this S superscript 0, which we know that we can use S superscript 0 to find delta S, right? But just finding the specific entropy isn't on the table. And that's why we need to use when we go from state 1. So now we're going to go from state 1 to state 2s, right? So here we got to remember that this is isentropic, right? So now, because we can't just look up, it's not that S superscript 0 stays constant, it's that S stays constant. So now we're going to have to use that P2S divided by P1 is equal to PR2S divided by PR1, right? So in this case, I know P2S over P1, that's the compressor pressure ratio. And because I knew the temperature here at state 1, then I use this to find PR2S. Now, once I have PR2S, then I use this to interpolate on A22. So from A22, I'm going to take this S right off the table, right? So here, I'm going to use table A22, and I'm going to interpolate to find H2S, and then I'm also going to interpolate here to find T2S. Now, as I go to the real turbine, right, so from S1 to S2S, I'm again going to use the compressor efficiency. I won't go through that again. It's going to be the same expressions, delta H over delta H, but now you're going to have H2S, and the only thing you're not going to have is H2, right? So from this equation, you're going to get H2. Right? And now, once you have H, so here you had H2S and you had T, right? And now you're going to have H2. And now with H2, you're going to interpolate on table A22. And from that, you're going to find PR2 and you're going to find T2. Right? Remember, we had all the pressures already just from looking at the problem. So now we're going to go to state 3. State 3 is kind of like state 1, right? So state 3, we know that P3 is equal to P2, and T3 is given. And because T3 is given, we can go to table A22, and we can find H1 and H3 and PR3. Right, so now we interpolated for that. So now from state 3, because we know this temperature, then we know this, and we know this. Now, this is going to be like going through the turbine. We're going to go from state 3 to state 4S. This is isentropic. So now P4S over P3 is going to be equal to PR4S over PR3. We're going to use this to find PR4S. Once we have that, right? So that gives us PR4S, right? And then we're going to go to table A22, right? This is why I didn't want to, go through this to get, although we're not getting numerical answers either way, I guess, right? But because we have this one piece of data, then we can get H4S and we can get T4S. So here, now we know this and we know this, right? And now we can use, as we go from state 3 to state 4, now we use the turbine efficiency just like we used before. And that turbine efficiency will give us H4. And once we know H4, then we could, if we wanted to, maybe we would just realize that we're done because all the expressions, the symbolic solutions, don't require us to know if we're doing variable specific heat. We don't care what T4 is, and we don't care what PR4 is. But if we wanted to, or if it explicitly asked, we could then find T4 and PR4. Right? So you don't necessarily have to fill in the boxes on the state table just because they're there. But here we use the thermal efficiency, right? And then from that we could get from here to here. So basically this, because we knew the temperature, we got H. Then we interpolated to get PR4. Then we used delta S is equal to 0 to interpolate to get H. Then we used the compressor efficiency to get T2. Right now, because we knew this temperature, we could find H, and then from H we could get PR, and then here we could say that delta S is equal to 0, and then once we knew this, we could interpolate back here, and then we could get the efficiency, use the efficiency of the turbine to get over there. So that's generally how you would do a Brayton cycle. Now, if we wanted to make the Brayton, so first, I guess, are there any questions about the process that we've used either in constant or variable specific heat? So there's a couple things that we could do here, right, to make this more complicated. We could add some intermediate pressure line in here. Whoops. And then we could say, okay, we go through one turbine, we reheat, right? So this would be from reheat. And then we could go through one compressor and we could intercool, right? And if we did that, we would have this, right? So this would be, this is the temperature that our exhaust would normally be, but we can take that exhaust and put it through a regenerator and have some, so regen, right? And then we would have to define the tricky thing about doing this, right? So if you did this, then this ends up being state 5 in a regenerator. So you have to think about the regenerator efficiency. So that's going to be the actual amount of heat through the regenerator divided by Q dot max, which turns out to be, so the regenerator would get you from here, which if we were numbering these, this would be 1, 2, 3, from 4 to 5. So this would end up being H4 minus H5 divided by the maximum amount of heat. So this would be 5, this would be 6, 7, 8, 9, and then there would be some exhaust temperature down here, state 10. So this would be the maximum amount of heat would be as if you could get this all the way up to H9. So this would be H4 minus H9. And actually, if you were getting this from the first law, this would actually be H5 minus H4 and H9 minus H4. But it ends up being the same no matter which way you flip those around. So that becomes important, this regenerator, because when you go through these different states, what will happen is, just like here, we kind of went through the compressor side, and then we went through the turbine side. and they gave us this maximum temperature in between. So if you get a really funky one like this, you'd be able to do the same things we did, just, you'd go through the first compressor, just like we did, but then there's some cooling at constant pressure, so you'd get some extra state over here, 3, right? So you'd reject some heat, and then you go through apparently, I don't know if you can see it, but my PC just cut out. So we would go through, I don't know why that happened. That's super weird. It's like my screensaver turned off. I think that my computer stopped sending a signal to that monitor. Oh, there we go. Right, that was kind of scary. Right, so what were we saying? So now we would go through this second compressor, and at this point, you would get to this regenerator part of the problem, and you would say, oh, I know H4. Maybe the problem gives you the regenerator efficiency, but usually when you get to this point, you don't know H5 and you don't know H9, so you're kind of like, oh no, I can't keep going. So at that point, when you feel stuck, what happens is you go to the inlet of the first turbine, because just like in this problem, they'll usually give you the temperature going into the first turbine. So you leave state 5 for a second, and then you go through the first turbine, and then you know something about the reheat. Maybe they tell you T8 too. You go through the second turbine, and then partway through the problem, you'll figure out H9. And then when you know H9, you come back into the regenerator, and then you say, okay, because I knew H9, then I knew H5, and then on the other side of the regenerator, you'll try to find the real exhaust temperature. And the real exhaust temperature, because this will say, all this real heat that went into the cold side of the regenerator had to come out of the hot side of the regenerator. So then you can find the exhaust temperature, right? Now, I know it's a little weird to just talk through that, but remember, we did do a problem like that in class. I think that the lecture number is, so this is from the summer lectures. So if you want to go back and watch the video for a Brayton cycle with improvements, that's going to be lecture 33. I'm not sure exactly where it is, but I think all of the pre-recorded lectures, not the live lectures, but the pre-recorded lectures are in one tab in the content section. So you can check that out. It's also if you go into the My Courses site and you check here, maybe I can bring up the My Courses site over here. If you go into My Courses, here, just let me log in here. Got a 2-factor identification. So if we go into the My Courses site, then we can see for content, if you want to find that lecture 33, you can either come to the pre-recorded lectures here and just find lecture 33. There's a lot of lectures in here. So 33, Brayton cycle with improvements. And the starter sheet for this is right here too. So you can sort of play along or do that problem. If you want a shorter version of that lecture, or at least the shorter version of that example, you can also go to the content and you can go down into Scherzer cycle analysis example videos. And these are broken down. So these are just kind of pre-recorded lectures, mostly with just the example problems for the different cycles. So here you can go to Brayton cycle problems and you can look at Brayton cycle improvements and click on that, and that'll take you to the YouTube video, right? So if you didn't know this was here, these are sort of shortened versions with all those example problems. So I think that that's all that I wanted to talk about. Does anyone have questions moving into tomorrow? So remember, we will have office hours tomorrow at 12.
I do have one quick question. I've been studying the videos on cycles, but what would you recommend looking at for the multiple choice section of the exam?
Yeah, I think so the multiple choice are broken into the 10 questions, right? So some of them are, I would say more than half of them are cycle analysis problems where maybe you'll get a picture of maybe a TS diagram or maybe a cycle sort of schematic like this, maybe with a state table that has some
And
information
you're asked
filled
to
out.
like solve like one small part
Yeah.
or whatever.
Yeah, right. So
Okay.
maybe if it was like this problem and I'd give you enough information to find the compressor, I'd say, oh, how much power across the compressor? And all the H values are listed here. Or maybe I would give you H2 and H2S and I would ask you, what's the efficiency? Right? So, or maybe I would just give you a TS diagram that looks like this and say like, what cycle is this from?
Oh, I see. Okay,
Right?
that makes sense.
Then there'll also be other types of questions that are just more definitional, right? So, looking through the quiz questions is probably a good idea to see some of those sort of throughout the course. So that I think would be my advice for the multiple choice type question.
All right, thank you.
Any other questions before we sign off? All right, everyone. Thank you. If I see you tomorrow, that's great. If I don't see you tomorrow, good luck. And I'll have a meeting at the back half of the exam. So good luck if I don't see you. Thanks. Bye-bye.